Welcome to This Explainer. Imagine, just for a second, a really high-stakes medical scenario. We're talking about an artificial pancreas implanted inside a patient. Now, if the biosensor inside that device miscalculates blood sugar levels, or if the patient's body flat out rejects the material, the consequences could be absolutely catastrophic. Designing a biosensor isn't just some abstract chemistry experiment you do for fun, it's quite literally a life-or-death engineering challenge. So today, we are going to trace a biosensor's journey from the lab bench out into the real-world market. Think of a newly developed biosensor kind of like an elite athlete. It might have this incredible, off-the-charts raw potential, but before it can actually compete on the world stage, it has to survive a really grueling series of performance tests.
Okay, let's dive right into our roadmap for today. We're going to start with Section 1, Precision, covering selectivity and detection. Then we'll move into Section 2, the Consistency Test, which is all about reproducibility. After that, Section 3, Racing the Clock, focusing on time factors. And finally, Section 4, making it commercially viable.
All right, let's step straight into Act 1 with precision, selectivity, and detection. In this first phase, we're really just testing the biosensor's raw skills to find its target molecule in a super crowded environment, and to detect it even when it's barely even there. Now, to really grasp selectivity, we have to look at the actual biological material doing the sensing. And here's a brilliant question straight from the science. Why do whole cells get interference? Well, if you use a highly purified enzyme, it generally only looks for one specific thing. It has tunnel vision. But if you use whole microorganisms or complex plant tissues as your biocomponent, you're suddenly bringing in a whole host of complex metabolic pathways. You're basically inviting interference from all sorts of other substances floating around in the sample. The sensor might get confused, react to the completely wrong thing, and completely ruin its selectivity. So once we know it's looking for the right thing, we have to figure out its detection limit. The official IUPAC definition is quite a mouthful. The concentration of the analyte at which the extrapolated linear portion of the calibration graph intersects the baseline. Okay, let's translate that dense language into plain English, shall we? Think of that elite athlete again, tensed up at the starting line. The detection limit is simply their ability to react to the absolute smallest, quietest possible sound of the starting gun. It's the lowest possible concentration of a substance that the sensor can confidently distinguish from just a zero baseline reading. Let's anchor that theory with a really concrete example. For blood glucose determination, the biosensor's linear range of response has to cover a very specific window. We're talking at least 2 times 10 to the negative 4 up to 2 times 10 to the negative 2 molar. By maintaining a highly predictable linear response right across the specific range, scientists can actually extrapolate backwards to hit a super precise detection limit of 10 to the negative 5 or negative 6 molar. If the calibration isn't linear here, well, the sensor is basically flying blind at those lower concentrations. Now, what's genuinely fascinating is how we actually measure sensitivity. It's directly inferred from the slope of that calibration plot we just talked about. A steeper slope means that an incredibly tiny change in concentration triggers a massive jump in the sensor's response. That's your high sensitivity. A flatter slope? That means low sensitivity. And this is such a brilliant way to judge different engineering choices. Like, if you want to know which method of attaching or immobilizing your enzyme to the transducer is actually the best, you just test them and compare their slopes. The steeper slope wins every time. Moving right along to Section 2, the consistency test, reproducibility. Look, hitting a bullseye once is just luck. Hitting it 1,000 times in a row, that is precision. We need to see if our athlete's performance is consistent enough to actually be valuable. You see, reproducibility is actually a two-part test. On one side of the coin, you have data reproducibility, meaning can the device spit out the exact same numerical result from the exact same sample time after time? But on the flip side, you have biological reproducibility. This means you're routinely checking if your purified enzymes still have their spark, or if your whole cells are still viable, and you're making sure the exact same amount of biomass is used every single time. Let me draw a very clear line in the sand here. If the biological preparation fails, your replicate data will absolutely fail alongside it. Biology is the very foundation of the data. So the golden rule of thumb here is this. For a biosensor to be taken seriously at all, the expected reproducibility between those replicate determinations really needs to fall within plus or minus 5 to 10%. Now sure, some highly sensitive clinical sensors might demand an even tighter margin, but this right here is your baseline standard, just to pass the consistency test. Let's move into Act 2 of our sensor's journey with Section 3, Racing the Clock, Time Factors. Here, we face the ultimate enemy of biology, time and decay. An athlete can't perform at their peak forever. And you know what? Neither can a biological component.
First up, we have to look at the immediate time factor, which is response time. Think of this as the settling down period. It's the time it takes for the whole biosensor system to reach a steady state of equilibrium so you can actually trust the measurement you're taking. Out in the real world, a few seconds to maybe 5 minutes is highly desirable. But if your sensor takes more than 10 minutes to reach equilibrium, no way. That's an automatic disqualification for any kind of repetitive routine analysis. It is just way too slow.
Let's see how this impacts things on the ground. It all kicks off with that response time, our athlete's pure reaction speed. But a sensor cannot just run sprints back-to-back forever. We absolutely have to factor in recovery time. This is the mandatory resting or recharging period that's required to make sure the sensor is completely clean, reset, and totally ready to accurately measure the next sample. And this brings us to the final equation that really matters. Response time plus recovery time equals the total number of samples that can be analyzed per hour. This is the ultimate metric that hospital administrators and environmental testers actually care about. It dictates whether or not the sensor is genuinely useful in a high-volume, high-stress setting. Beyond that rapid minute-to-minute race, there is a much larger macro race against time, the overall lifetime of the sensor itself. Take a quick second and mentally rank these biological materials for me. Enzymes, microbial cells, and plant tissue. Which one do you think burns out the fastest? The harsh reality is that all biological materials naturally degrade over time. This limited lifetime is honestly one of the major drawbacks of biosensor technology, simply because it forces developers to constantly replace parts, which of course drives up maintenance and costs. When engineers sit down to calculate a sensor's lifetime, they actually have to measure 3 very distinct aspects. First, the lifetime of the sensor while it is actively being used. Second, its lifetime just sitting in storage on a shelf. And third, the lifetime of the biomaterial when it's stored completely separately from the hardware. Think of those disposable blood glucose strips kept in a little vial, totally separate from the electronic meter. Because biological lifespans are so finite, developing cheap, single-use, disposable biosensors is very often the most logical, cost-effective route for developers to take. But hey, there are some pretty incredible exceptions to biological decay. Take glucose oxidase in its freeze-dried or lyophilized form. It is remarkably stable. We are talking survival for 2 years at 0 degrees Celsius and an astonishing 8 years at negative 15 degrees Celsius. But, and there is a massive but here, there's a catch. This is only true in its purely isolated form. The exact moment you start adding stabilizers, additives, or immobilization materials like graphite powder to build the actual functional sensor, that impressive lifespan usually plummets. All right, let's transition to the climax of our story, Act 3, with Section 4, making it commercially viable. Our sensor has proven it's precise, it's consistent, and it's fast in the lab. But now it has to prove it can survive the brutal, unforgiving reality of the commercial market. Here is the absolute mountain of real-world requirements that developers are up against. Having brilliant science is just no longer enough. To be commercially viable, this thing has to be cheap to produce, it absolutely must be portable, it needs to be incredibly user-friendly, like requiring basically 0 training. If it's a medical device, it really should be non-invasive. It has to use tiny, microscopic amounts of expensive biomaterials to keep the cost down. And it has to function perfectly at physiological pH. Because let's face it, clinical success in a pristine, climate-controlled lab means absolutely nothing if a totally exhausted nurse or an elderly patient in their living room can't easily and reliably use the device. Let's look at the specific requirements for environmental field applications, just to give you a sense of this shift from abstract science to hard commercial constraints. Look at the cost. We're talking RM5 to RM80 per analysis. Look at the portability. It has to be compact, with 0 external power required. Assay times need to hit that sweet spot between 1 and 60 minutes. The sensitivity still has to be phenomenal. We're talking parts per million or parts per billion, but it has to do all of that while being operated by someone with minimal training, standing in a muddy field, not a PhD scientist in a sterile lab. Which brings our explainer full circle, right back to that high-stakes medical hook we started with, the artificial pancreas. This device represents the absolute peak of commercial and biological requirements smashed together. Not only does it have to be perfectly precise, perfectly consistent, and incredibly fast, but it also has an extreme, non-negotiable real-world constraint. It must be biocompatible.
It has to physically survive inside the human body for weeks without triggering an immune rejection, all while continually, flawlessly delivering data. So, we've seen exactly what it takes for a biosensor to earn its place in the real world. And as you can tell, it is an incredibly difficult hurdle to clear. So, I want to leave you with this final thought. The next time you're scrolling and you see a flashy headline about some miraculous new medical sensor or a crazy environmental breakthrough developed in a university lab, I want you to look past the hype. Think back to this exact checklist. Ask yourself, is it reproducible? Is it fast? Is it actually cheap to make? Ultimately, can it really survive that brutal journey from the lab bench to the market? Keep that critical lens sharp, folks. Thanks so much for joining me on this explainer.